An event of such magnitude where the asteroid or the comet that hits is of several kilometers in diameter has occurred on Earth in a recurrence interval that is about tens to hundreds of thousands of years. So again, that would be something like this one right here. So you see that this graph is pretty cool. It has the typical interval between events. So this would be the years in between that we would expect them to occur. It has the explosive powers in millions of tons that it would exert. So again, this one was, I think, over 10,000 times the amount of nuclear power we had on Earth. And then here you have the asteroid or comet diameter per se. So we had said that this particular one was 6 kilometers in diameter. So 6,000 would be the case. Okay, so smaller objects on the order of just a few tens of meters, so that would be over here, if they produced an airburst or a surface impact near a populated area, would cause a regional catastrophe. The area would probably be devastated, and it would be on the order of several thousand of square kilometers. An example for this type of event would be something like the Tunguska event that happened in 1908 in Siberia, but in a more populated area, it would cause a lot of chaos. An event like this one, so an airburst from asteroids with diameters of about 50 to 100 meters, are actually capable of causing catastrophic damage to a region about every 1,000 years or so. So recently, with computer-run simulations, we have been able to suggest that during a given century, approximately 450 deaths per year may be attributed to an impact. And these numbers are based on averages. So these are based on the probability of an asteroid or a comet or a meteoroid going into the atmosphere. They're based on population, and they're based on areal distribution, and on the energy that they could release overall. So, of course, a large event could kill millions of people, but if we average it out over the years, the likelihood of them occurring will result in the death toll of about 450 people per year. It was really not until recently that the risk of impacts has been assessed by scientists and policymakers. So, are we really helpless, or is there something that we can actually do when we talk about minimizing the hazard? The first thing to be done is really to identify nearby objects in our solar system that might threaten the Earth. So, identification and classification of asteroids and comets that cross Earth's orbit are already in progress. And they can even account for smaller objects such as meteoroids. Spacewatch, which is a program that has been running since 1981, does the inventory of said objects, and is actually expanding to account for other solar systems objects as well. Another program, which is called the Near Earth Asteroid Tracking, or NEAT, was started in 1996, and this program's objectives are to study the size distribution as well as the dynamic processes associated with the near-Earth objects, also referred to as NEOs. So I'm going to refer to that a lot. And specifically, it is to identify those objects with a diameter that are under 1 kilometer in size. So, near-Earth objects, or NEOs, either reside and orbit between Earth and the Sun, or they have orbits that intersect the Earth's orbit. From the NEOs, only comets and asteroids are truly threatening. The meteoroids are typically small enough that the hazard would not be as high, such a Tunguska type event. However, if the NEOs that impacted or airbursted were several kilometers in diameter, that would cause a global catastrophe, as we have seen from previous examples. Okay, so as I mentioned earlier, most asteroids originate in the asteroid belt that is located between Mars and Jupiter. The asteroid only becomes a near-Earth object if it gets disturbed by a collision or by the gravitational pull of Jupiter, for example, which is really large, and it will tend to do this. And it will make the orbit of the asteroid more elliptical and perhaps cross Earth's orbit. Currently, the estimate of Earth crossing asteroids with diameters larger than 100 meters is close to 85,000 of them. The estimate for asteroids larger than 1 kilometer in diameter is about 1,100 of them. And then lastly, the estimate of asteroids as near-Earth objects that are larger than 5 kilometers in diameter is only about 30 of them. Comets, which are the other type of near-Earth object, or potentially the other type of near-Earth object, are generally few kilometers in diameter and have an expanding stream of gas and dust that produces a spherical cloud around the comet, as we know. It typically also has a tail of gas and dust, and though the tail itself is blown out from the cloud by the force of solar radiation, which makes the tail always be directed away from the sun. Many of the dust and the gas particles that are within the comet will burn up in the atmosphere when the Earth's orbit passes through the comet's tail, which creates a stream of meteors, which we call a meteor shower. Of the 10,000 NEOs identified as of July 2013, only 93 objects have a gaseous tail when they approach the sun, and so only 93 of those 10,000 are classified as comets. 15% of the 10,000 are thought to be extinct comets that are no longer generate a tail because all of the gases and dust particles are pretty much gone, and so they no longer get that tail from the heat of the solar radiation. Near-Earth objects, whether they are asteroids, comets, or meteoroids, apparently have a pretty short lifespan, so many must be continuously pulled out from the asteroid belt to explain their abundance still as near-Earth objects. Or they must come from somewhere else in the solar system as their orbit changes in the case of comets, for example, that don't come from the asteroid belt, but rather come from the Oort cloud or somewhere else in the solar system, and their orbit might just be changing little by little. Alright, so by estimates, about 20 million extraterrestrial bodies in the near-Earth orbits have the potential for a significant impact. 20 million of them. Only 4% of those 20 million are likely to penetrate the Earth's atmosphere and excavate a crater. So that's not too many, I guess. And more than half of those 20 million are weak and are prone to explode at altitudes of about 30 kilometers above the surface. So that would pose no threat, really, to the surface area. And the remaining 40% or so are moderately strong or stony asteroids that could penetrate the atmosphere and produce a serious threat at the surface, or produce some sort of airburst like the Tunguska type event that we saw. So identifying and tracking all objects, especially those with diameters of only several to thousands of meters, is actually very challenging. We are currently incapable of cataloging the estimated 10 million small asteroids and comets that there are out there. However, we are pretty good at tracking the large ones. So those would be ones that have a few hundred meters in diameter. So we're getting better and better, but it's still very challenging. So once a large near-Earth object is recognized to be on a collision path with our planet, the options available to avoid or perhaps to minimize the hazard from an event like that are pretty limited in truth. The area that would be impacted is due for a pretty fast demise. The rest of the world for a pretty bad demise, if you would, because it would be much slower and perhaps a more painful one. However, a near-Earth object of diameters of hundreds of meters could be dealt with, kind of. So if we could identify and blow the object apart, basically, that would probably bring more problems than it would solve in truth. So a better approach would be to try to gently divert the object, to move it from its current orbit. So currently, we have the technology to change the orbit of a threatening asteroid with what is small nuclear explosions that are close enough to the asteroid to nudge it, but still far enough away to avoid breaking it up. So this alternative has been identified by far as the most effective one, but other alternatives of still diverting its orbit have been proposed, like pulse laser or focused laser radiation, which have been on the table. But again, the nuclear explosion one, I think, is 10 times better than the other two. So if we were able to do this, it would cost something like $1 billion or exceed the $1 billion mark, and it would require a lot of coordination and cooperation between the world's military and the space agencies. But this would be better than the alternative, right? Another alternative for a small event would be evacuation, if we were able to predict the point of impact months in advance. So theoretically, we could be doing this because we're pretty good at tracking these by now. And so theoretically, we could evacuate that amount of people in time. However, this would be incredibly expensive, perhaps exceeding the $1 billion, and it would be a tremendous and likely impossible undertaking that we would take. So, overall, as astronomers continue to catalog these extraterrestrial objects and that intersect the Earth's orbit, so the near-Earth objects, we begin to think about the options to minimize the hazard that these could bring, were they to airburst or to impact us directly. Thankfully, we would potentially have a pretty long-term warning, since we are good at tracking these and checking when they would be able to impact us. But the long-term warning would aid in coming up with possible methods to intercept or minimize the hazard by, say, nudging it, as we said, so that it pretty much misses the Earth. Okay, and so with that, we are done covering chapter 14. I really enjoyed reading through this chapter and learning a little bit more about the extraterrestrial objects, which I did not know so much about. I hope you also learned a lot, especially about the mass extinctions, which was the topic that I mostly wanted to cover as part of this course. So, as always, I am here if you have any questions. Be on the lookout for the activities and the labs associated with this chapter as well.